All right, let's talk about the future of heating and cooling. And I don't mean just slightly better air conditioners. We're talking about a complete rethinking of how we manage temperature, something that's becoming absolutely necessary on a global scale. And this is exactly why. Whether it's in our homes or in massive factories, controlling the temperature puts this huge constant pressure on our energy grid that most of us never even think about. The way we're doing things now, it's just not going to work long-term. So here's how we're going to break this all down. First, we'll dig into the problem itself. Then we'll explore the wild new idea that's driving a solution. We'll look at the actual tech, see how it performs in the real world, and then map out what it's going to take to get these things out of the lab and into our lives. Okay, so let's start with the big question. Why? Why are so many brilliant people trying to completely reinvent something as fundamental as heating and cooling? Well, it really just boils down to a massive problem of scale. Take a look at this number, 280%. That's the projected spike in just residential cooling demand by the middle of the century. You can just imagine the kind of stress that's going to put on our electrical grids. It's almost unbelievable.
And here's the thing. We can't just chip away at this problem with small tweaks. The basic technology in our air conditioners, the vapor compression cycle, has been around for 100 years. Yeah, it's gotten better, but it's pretty much hitting the limits of what it can do. To deal with that 280% jump, we need a whole new playbook. We need a step change.
And this is where we get to a really fascinating, almost backwards-sounding idea. What if we could use heat itself as the fuel to make things cold? That's the big idea behind something called a thermally driven heat pump, or TDHP. It completely flips the script. It takes a heat source, and this could be waste heat from a factory or even just hot water from a solar panel, and it uses that energy to run the whole show.
Now, what's so cool here is the difference in the kind of energy being used. Your standard heat pump uses electricity. That's high-quality, very valuable energy to power a big mechanical compressor. But a TDHP, it can run on low-quality heat, the kind of energy we are literally just venting into the atmosphere every single day. It's an incredible shift. So how in the world does it work without that compressor? The easiest way to picture it is with a sponge. Imagine you have this special material that just loves to soak up refrigerant gas, kind of like a sponge soaks up water. That's step one. Then you add heat. The heat acts like you're squeezing the sponge, forcing all that refrigerant out as a high-pressure gas. And it's that pressure, created by heat, not a motor, that powers the whole cooling cycle.
And here's what our simple sponge analogy looks like to an engineer. Now, don't worry about the fancy terms. Just follow the circle. You start with adsorption, that's the sponge soaking everything up. Then you add heat, which builds pressure. That leads to desorption, squeezing the sponge. That high-pressure gas goes off, does its cooling job, and then the whole system cools down and starts the cycle all over again. It's this elegant, continuous loop, all driven by heat. Okay, so that's the core idea. Pretty cool, right? But now let's get into the specifics of how this is actually being done. Thermally driven is a big umbrella, and there are a few really interesting technologies living under it. This table gives us a great bird's-eye view of the three main paths. First up is absorption, with a B, that uses a liquid sponge. Then there's adsorption, with a D, which uses a solid material. And finally, you've got solid-state technology, which is a whole different ballgame. It uses electric or magnetic fields to directly change a material's temperature. Let's dig into that solid-state idea for a second, because it's just amazing. This diagram is showing us the entropy, or the amount of disorder inside a material. Think of it like a messy room. When you apply a field, you're basically forcing all the atoms to line up perfectly. You're cleaning the room. And that act of ordering things actually releases heat. Then, you turn off the field. The atoms all go back to being messy. And to do that, they have to suck up heat from their surroundings, which makes everything around them cold. You're creating heating and cooling just by organizing atoms. How cool is that?
So, we have these incredible concepts, right? But a great idea is one thing. Real-world performance is something else entirely. How do these new technologies actually stack up against the systems we already have?
The way we measure this is with something called the coefficient of performance, or COP. It's actually really simple. For every 1 unit of energy you put in, how many units of cooling or heating do you get out? A COP of 3 means you get 3 units of cooling for 1 unit of energy. So, higher is always better.
And this chart, well, it tells a fascinating story. On the left, you've got the absolute best conventional heat pumps you can buy today, maxing out at a COP of about 5.5. In the middle, you see a typical absorption system. It's lower, around 1.5,
But remember, it's running on cheap or even free waste heat. But then, look all the way to the right. The theoretical potential of some of these solid-state systems is a COP of 10 or more. That's the game changer we've been talking about.
But we do have to ground ourselves in reality here. This chart shows us the number of research papers published on different materials. And you can see that metal organic frameworks, or MOFs, which are some of the most exciting new materials, they're still just a tiny sliver. Most of the work is still happening on older materials. So we're definitely still in the early innings.
Which brings us to our final and maybe most important section. How do we get from a cool material in a science lab to a reliable machine you can install in your home? What's that journey actually look like?
This timeline gives us a really good snapshot. Absorption systems, they're already here. You can buy them commercially today, mostly for big buildings. Adsorption systems with those fancy MOF materials, they're at the prototype stage. They exist, they're being tested right now. And solid state, that's a bit further down the road. The materials are showing incredible promise, but building a whole system around them is the big research project for the next decade.
And getting to the finish line means clearing some pretty big hurdles. First, that COP number, the efficiency, it needs to get better to compete. Second, just the physical challenge of designing heat exchangers for these solid materials is a really tough engineering problem. Third, cost. Advanced materials like MOFs are still way too expensive to mass produce. And finally, there's just the massive leap from having a cool material to having a complete, reliable, affordable system that works for years. These are the big puzzles that researchers are working on as we speak.
So all of this leaves us with a really powerful idea to chew on. In a world that's getting hotter, the very heat that we're currently just wasting could become our single best tool for keeping ourselves cool. It's a complete shift in thinking, and it's one that might just change everything about our energy future.